Picture this: a star, billions of years old, glowing with the heat of nuclear fire, suddenly wrenched from its peaceful orbit. An invisible force, so powerful it bends space itself, pulls the star apart like taffy, stretching it into a swirling, screaming ribbon of light. And then silence. The star vanishes, swallowed whole by the cosmos' most terrifying predator, a black hole. This isn't science fiction. This is the universe reminding us just how small and how fragile we really are. Out there, beyond the safety of our blue planet, lies a cosmos filled with wonders and nightmares, forces so violent they could erase us in an instant, objects so bizarre they defy logic, and phenomena so destructive they make supernova look like firecrackers. Today, we're venturing into the darkest corners of space to uncover the 25 most dangerous objects in the universe. From rogue planets hurtling through the void like cosmic bullets, to gamma-ray bursts, nature's own death rays capable of sterilizing entire galaxies. This isn't just a list, it's a journey to the edge of annihilation. But why should we care? Because the universe isn't just a pretty light show. It's a battlefield, a place where the laws of physics unleash chaos on scales we can barely comprehend. And yet, understanding these dangers isn't just about fear, it's about awe. It's about realizing how lucky we are to exist at all, on a tiny rock shielded by atmosphere and distance from the horrors lurking in the dark. So buckle up. By the time we're done, you'll never look at the night sky the same way again. Rogue black holes are the universe's ultimate ghost stories, cosmic phantoms drifting unseen through the void, their presence betrayed only by the destruction left in their wake. Unlike their stationary cousins at the centers of galaxies, these monsters don't stay put, they roam. Born from the collapse of massive stars, they start with a violent death, a supernova so powerful it crushes the star's core into an infinitely dense point, a singularity where gravity becomes a prison from which not even light can escape. But sometimes the explosion isn't symmetrical. A lopsided supernova can kick the newborn black hole like a cosmic bullet, sending it careening through space at hundreds of thousands of kilometers per hour. Imagine one silently gliding through a star system. At first, nothing seems wrong. Then planets begin wobbling, their orbits twisting in ways that defy explanation. Moons spiral inward, gas and dust ripple as if tugged by invisible fingers. By the time anything gets close enough to cross the event horizon, the point of no return, it's too late. The black hole's gravity stretches and shreds everything into a swirling disk of superheated plasma, a last scream of energy before vanishing forever into the dark. The terrifying part, we might not see it coming. Black holes don't emit light. We detect them by the way they warp space around them or the X-ray glow of their victims. A rogue black hole could be halfway through our solar system before we realized it was there. Some astronomers even speculate that one could have already passed unnoticed through the outer reaches of our cosmic neighborhood, its gravity subtly tugging at comets and dwarf planets without us ever knowing. And yet, for all their horror, rogue black holes are also mesmerizing. They're reminders of how dynamic and chaotic the universe truly is, where even the most monstrous objects are just passengers carried along by the same forces that shape galaxies and spin worlds into existence. But that doesn't make them any less deadly. Out there, somewhere in the dark, one could be drifting toward another unsuspecting star system right now, hungry and utterly invisible. What if one of these cosmic predators wandered into our solar system? The danger wouldn't come from the black hole itself, at least not at first. A rogue black hole the size of our Sun could pass within Pluto's orbit without swallowing anything, its gravitational reach too small to consume planets outright. But that's where the good news ends. Its presence would send chaos rippling through the solar system like a pebble dropped into a still pond. First, the subtle distortions. Neptune's orbit might wobble inexplicably. the Kuiper belt, that icy graveyard of comets, would shudder under the unseen tug, sending some of those frozen bodies spiraling inward toward us. By the time astronomers noticed the anomaly, Earth could already be in the crosshairs of a newly destabilized comet swarm. Then the tides, even from a distance, the black hole's gravity would stretch and squeeze our planet, amplifying earthquakes and volcanic activity. The Moon, our faithful companion, might be ripped away entirely, sent careening into space, or shattered into a temporary ring of debris. Detection nearly impossible until it was too late. Current telescopes can't spot an isolated black hole unless it's actively feeding, and by then, the distortions in nearby starlight would be the least of our worries. Some theories suggest we might detect tiny shifts in the orbits of distant probes like Voyager, their paths bending just slightly off course. Other models propose watching for gravitational microlensing, a brief brightening of background stars as the black hole's gravity warps their light like a funhouse mirror. But these are needles in a galactic haystack. Survival, forget hiding underground or fleeing to Mars. If a rogue black hole came close enough to threaten Earth directly, we'd have one option: evacuate the planet entirely. Even a near miss would destabilize Earth's orbit, potentially turning our world into a frozen wasteland or a scorched hellscape. The only hope would be detecting the threat early enough to launch generational arcs into the void, assuming we could build them in time. Yet for all the doom, there's a strange beauty in this scenario. The same forces that could doom us also sculpt the universe, those swirling tides of space-time. They're what shaped galaxies in the first place, the incomprehensible power of a singularity. It's a reminder that the cosmos operates on scales beyond human reckoning. We're just temporary guests in a house where the walls bend, the floors melt, and the doorways lead to places where physics itself breaks down. And that's the real terror, not that the universe is hostile, but that it's indifferent. A rogue black hole wouldn't hate us, it wouldn't even notice us, and that's what makes it so chilling. If black holes are the universe's silent assassins, magnetars are its screaming berserkers, cosmic lighthouses broadcasting death across the galaxy. Born from the collapse of massive stars, these neutron stars pack the mass of a sun into a city-sized sphere, spinning faster than a blender blade. But their real terror lies in their magnetic fields, forces so intense they defy comprehension, quadrillions of times stronger than Earth. A magnetar's pull is so powerful it would liquefy your atoms from 1,000 kilometers away, ripping the electrons right off your body before you even knew what was happening. Now picture one of these monsters having a tantrum. As the magnetar's crust strains under unimaginable magnetic pressure, it cracks, a starquake. This isn't like an earthquake. It's a seismic event on a nuclear scale, releasing energy equivalent to 100 billion atomic bombs in a fraction of a second. The explosion twists spacetime itself, sending out a gamma ray burst so bright it outshines entire galaxies for a heartbeat. Any planet within a dozen light-years would be sterilized instantly, its atmosphere shredded by the magnetic storm like tissue paper in a hurricane. In 2004, a magnetar 50,000 light-years away released a burst so powerful it compressed Earth's magnetic field and ionized our upper atmosphere from halfway across the Milky Way. The scariest part, we've only detected a handful of magnetars, but there could be thousands lurking in the dark. One nearby event could end life on Earth without warning. Even our sun's protective heliosphere would be useless against such a blast. And yet, magnetars aren't just destroyers, they're cosmic laboratories, places where matter warps into impossible shapes under magnetic fields so strong they create magnetic spaghetti, strands of atoms stretched into bizarre quantum knots. These objects remind us that the universe doesn't just kill with gravity or collisions. Sometimes it reaches out with an invisible hand, so powerful it can erase worlds without touching them. Magnetars are proof that in space, even emptiness can be weaponized. December 27, 2004, a normal day on Earth until an invisible tidal wave of energy slammed into our planet without warning. It came from 50,000 light-years away, a pulse of gamma rays so powerful it briefly outshone our entire Milky Way galaxy. The source, magnetar SGR 1806-20, a city-sized corpse of a dead star with a magnetic field strong enough to rewrite the rules of physics. This wasn't just a flare, it was a cosmic scream. In 1/10 of a second, the magnetar released more energy than our Sun emits in 150,000 years. The blast compressed Earth's magnetic field like a soda can, violently shaking charged particles in our ionosphere. Satellites in low Earth orbit glitched. Radio communications sputtered. GPS systems critical for navigation, banking, and emergency services flickered as if the planet had suffered a global power surge. And all of this from an explosion halfway across the galaxy. To grasp the scale, picture this: the strongest solar flare ever recorded, the Carrington event of 1859, unleashed enough energy to fry telegraph wires and spark auroras visible near the equator. SGR 1806-20's eruption was 100 million times more powerful. If this magnetar had been just 20,000 light-years closer, still cosmically distant, its gamma rays would have obliterated Earth's ozone layer, triggering mass extinctions. What caused such madness? Deep inside the magnetar, magnetic fields twisted like rubber bands stretched to breaking point. When the star's crust finally cracked under the strain, the entire structure recoiled, vibrating like a gong struck by the gods. This starquake unleashed a firestorm of particles accelerated to near light speed, their paths spiraling wildly along the magnetar's unimaginable magnetic field lines. The result, a light show visible across the universe and a chilling warning. Here's the terrifying truth: we got lucky. 50,000 light-years is a safe distance. But our galaxy holds thousands of magnetars, some far closer. One in the Orion Arm, just a few thousand light-years away, could erase modern civilization in an instant. No fireball, no impact, just a silent wave of radiation frying electronics, scrambling power grids, and turning our atmosphere into a radioactive chemistry set. Yet amid the danger lies awe. These outbursts are nature's ultimate particle accelerators, forging elements and energies we can't replicate on Earth. They're reminders that the universe doesn't just create, it destroys, reinvents, and reminds us how small we truly are. That gamma-ray blast in 2004. It wasn't aimed at us, it didn't even know we existed, and that's the most humbling part. Gamma-ray bursts are the universe's ultimate fireworks, cosmic explosions so violent they make supernova look like birthday candles. In just a few seconds, a single GRB can unleash more energy than our Sun will emit over its entire 10 billion-year lifetime. These aren't just flashes in the dark, they're death rays on a galactic scale, capable of sterilizing entire star systems in the blink of an eye. Picture this: two neutron stars, remnants of dead suns locked in a gravitational tango, spiral closer and closer until they collide. The impact creates a shockwave so powerful it rips spacetime itself, sending twin jets of plasma screaming outward at nearly the speed of light. These jets, narrower than a pencil but hotter than a trillion suns, punch through the cosmos like celestial blowtorches. If one were pointed at Earth, we'd never see it coming. The first sign would be a flash brighter than 1,000 full moons, gamma rays shredding our atmosphere, igniting global wildfires and stripping away the ozone layer in minutes. The aftermath, a planet bathed in lethal ultraviolet radiation, its surface scoured clean of complex life. The terrifying reality is this has likely happened before. 450 million years ago, the Ordovician extinction wiped out 85% of marine species. Some scientists believe a GRB just 6,000 light-years away could have been the culprit, a short, sharp burst of radiation turning Earth's oceans into toxic soup. Even more chilling, we've detected GRBs over 13 billion light-years distant, meaning these catastrophic events were occurring when the universe was barely a toddler. What makes GRBs uniquely horrifying isn't just their power, it's their unpredictability. Unlike asteroids or solar flares, there's no way to see them coming until the radiation actually hits us. The beams are so focused that by the time our satellites detect the initial gamma-ray spike, the lethal X-ray afterglow would already be en route. We might have mere minutes before an invisible tsunami of high-energy particles turned our technology to confetti and our skies into a radioactive haze. Yet amid the devastation lies a cosmic irony. GRBs might also be the architects of life. The same heavy elements forged in these collisions, gold, platinum, uranium, were later incorporated into planets like Earth. The very explosions that could erase civilizations also scattered the stardust that made them possible. It's a reminder that the universe doesn't operate in moral terms of good and evil, just cause and effect, creation and destruction woven into the same violent tapestry. And somewhere out there, right now, two neutron stars could be circling each other in their final deadly dance, completely unaware that their collision might one day light up the sky of a world billions of light years away, with consequences we're only beginning to understand. 450 million years ago, Earth teemed with life trilobites scuttling across ancient seabeds, towering reefs built by strange, fern-like creatures, and the first primitive fish venturing into uncharted waters. Then catastrophe struck. The Ordovician period ended abruptly in what became Earth's first mass extinction, wiping out 85% of all marine species. For decades, scientists blamed glaciation or volcanic activity until a radical theory emerged. What if the real culprit wasn't on Earth at all, but a gamma-ray burst from a distant, dying star? The evidence is eerily compelling. Fossil records show a sudden, simultaneous collapse across ecosystems worldwide, with no telltale signs of asteroid impacts or volcanic winters. Instead, layers of sediment reveal a spike in ultraviolet damage, as if something stripped away Earth's protective ozone layer almost overnight. Enter the GRB hypothesis. A burst just 6,000 light-years away could have bathed our planet in lethal radiation for less than 10 seconds, yet the aftermath would have been apocalyptic. The gamma rays alone would have ignited nitrogen in the atmosphere, creating toxic nitrogen oxides that devoured the ozone for years. Sunlight, once life-giving, would have mutated into a deadly weapon, scorching land and sea with UV levels rivaling the surface of Mercury. Modern detection adds chilling credibility to the theory. In 2008, NASA's Swift satellite observed a GRB so bright it was briefly visible to the naked eye, from 7.5 billion light-years away. Scale that down to a nearby burst like the one proposed for the Ordovician, and the energy would be unimaginable. Astronomers now scan fossilized plankton for radiation damage, hunting for atomic fingerprints left by gamma rays. Some samples show bizarre mutations consistent with extreme UV exposure, as if entire populations were flash-fried by an invisible cosmic strike, yet controversy lingers. Critics argue that GRBs are too rare to explain Earth's extinctions, with statistically only one likely to hit our galaxy every few million years. Others point to chemical traces of volcanic gases in Ordovician rocks, suggesting a slower terrestrial doom. But here's the haunting twist: both could be right. A GRB might have delivered the initial blow, weakening ecosystems just as climate shifts and toxic oceans finished the job, a one-two punch from the cosmos and Earth itself. What makes this theory so gripping isn't just the science, it's the implications. If a single stellar explosion reshaped life's trajectory once, it could happen again. Right now, somewhere in the Milky Way, two neutron stars might be spiraling toward collision, or a hypernova could be priming its death scream. We'd have no warning until the light and the radiation arrived. The Ordovician extinction isn't just ancient history, it's a test case for how fragile our biosphere truly is. And in a universe where stars can flicker out with the power of a billion suns, we're still just passengers on a pale blue dot, bathed in the afterglow of cosmic violence we're only beginning to understand. Deep in the cosmic archives, quasars burn like furious beacons, monuments to an era when the universe ran wild with energy. These aren't just bright objects, they're time capsules from the early cosmos, powered by supermassive black holes with appetites so voracious they outshine entire galaxies. Imagine a single point in space, no larger than our solar system, radiating the light of a trillion suns. That's the terrifying brilliance of a quasar, an engine of destruction running on the raw power of spacetime itself. At their core lies a nightmare made real, a black hole billions of times more massive than our sun, gorging on gas, dust, and whole stars. As this cosmic feast spirals inward, friction heats the material to millions of degrees, transforming it into a glowing accretion disk hotter than the heart of a supernova. But the real horror lies above the poles, where magnetic fields twist into coils tighter than a hangman's noose. Here, particles get whipped to nearly the speed of light and fired into space in jets so precise they could pierce a planet from 1,000,000 light-years away. These relativistic death beams carry enough energy to vaporize entire star systems, stripping away atmospheres and boiling oceans before the light from the explosion even reaches the victims. Quasars didn't just exist, they dominated. In the universe's chaotic youth, they were the apex predators, their jets carving vast voids in the cosmic web. One particularly violent specimen, SDSS-J 110-6+1934, holds the record for the most energetic outflow ever observed, a storm of particles blasting outward with the force of 100 million supernova. If our Milky Way hosted such a monster, its jets would stretch to Andromeda and beyond, a lethal bridge of radiation across the intergalactic dark. Yet there's haunting beauty in their rage. Quasars helped shape the universe we know today. Their outflows enriched the cosmos with heavy elements forged in the furnaces of their accretion disks. Their light, traveling billions of years to reach us, serves as a roadmap to the past, revealing how galaxies grew around these ravenous hearts. The brightest quasar ever discovered, J0439+1634, shines with the luminosity of 600 trillion suns, an eye-watering glimpse into an epoch when the universe burned hotter and fiercer than we can comprehend. Today, most quasars slumber, their black holes starved of fuel, but their legacy lingers. Every massive galaxy, including our own, likely hosted one in its fiery youth. The supermassive black hole at the Milky Way's center, Sagittarius A star, is just a quiet remnant of that violent past, a sleeping giant that once might have roared across the cosmos. That's the unsettling truth quasars reveal. Even the calmest corners of space were forged in chaos, their quiet beauty born from ancient cataclysms we can barely imagine. Some stars don't just burn, they flee. Hypervelocity stars are the universe's runaway bullets, hurtling through the void at speeds topping 2 million miles per hour, fast enough to cross the entire United States in less than a second. These aren't gentle wanderers, they're cosmic fugitives, violently ejected from their homes by gravitational forces so brutal they defy imagination. Take He 0437-5439, a rogue star caught in the act of escaping our galaxy. This blue giant, twice as massive as our Sun, rockets through space at nearly 1.6 million miles per hour, so fast it's not just leaving the Milky Way behind, it's punching straight into the emptiness between galaxies. Its crime, getting too close to the supermassive black hole at our galaxy's core. Picture this, a star swings near Sagittarius A star, its path bent by the black hole's gravity. But if another star happens to be orbiting nearby, the three-body interaction becomes a cosmic slingshot. One star gets captured, spiraling toward doom, while the other is flung outward like a stone from a trebuchet, accelerated to speeds that defy stellar physics. The danger isn't just their speed, it's where they're aimed. A hypervelocity star doesn't travel alone. It drags a comet-like tail of gravitational disturbance, potentially knocking asteroids or dwarf planets out of stable orbits in any system it passes. Worse, some hypervelocity stars come paired with deadly companions. Imagine a white dwarf, the dense corpse of a dead star, ejected at these velocities. If it collided with another star system, the impact could trigger a supernova, a stellar explosion with no warning, lighting up the sky with the force of 1 billion nuclear bombs. But the true horror lies in their origin story. Many hypervelocity stars likely began as part of binary systems, two stars orbiting each other peacefully until a galactic collision tore them apart. When the Milky Way eventually crashes into the Andromeda Galaxy billions of years from now, the resulting chaos could birth thousands more of these stellar outcasts, turning entire regions of space into shooting galleries. Yet for all their destructive potential, hypervelocity stars are also cosmic messengers. Their trajectories map the invisible gravitational currents of the universe, revealing the presence of dark matter and the tug of hidden black holes. Some might even carry hitchhiking planets, frozen worlds ripped from their orbits and sent careening through intergalactic darkness. It's a reminder that in space, even the simplest laws of motion can birth monsters, and that the same forces that fling stars into the abyss might one day send one hurtling straight toward us. A world without a sun drifts through the endless night, a rogue planet, exiled from its star system and condemned to wander the interstellar void forever. These cosmic orphans form just like any other planet, only to be violently ejected by gravitational chaos, flung into the darkness by a passing star or the death throes of their own system. Imagine Earth ripped from the sun's warmth, its oceans freezing solid within millennia, its atmosphere collapsing into icy dunes on a lifeless surface. That's the fate of most rogue planets, frozen tombs adrift in a sea of blackness, but some might defy the odds. Deep beneath icy crusts, tidal forces from a planet's own molten core could maintain subsurface oceans liquid water trapped for billions of years, shielded from the cold. In these lightless abysses, extremophile life might cling to existence around hydrothermal vents, much like the ecosystems at Earth's deepest ocean trenches. Now picture such a planet drifting into a new solar system, its icy shell melting under the warmth of an alien star. The result, a biological time bomb seeding a foreign world with microbial stowaways. It's called panspermia, the theory that life hitchhikes across the cosmos on asteroids, comets, or in this case, an entire rogue planet. The danger isn't just contamination, it's chaos. A rogue planet entering a stable system wouldn't announce itself politely. Its gravity would act like a wrecking ball, perturbing the orbits of other worlds. Astronomers estimate that for every star in the Milky Way, there could be 20 rogue planets, meaning our solar system might have already endured close calls we'll never know about. In 2018, researchers detected a potential rogue planet just 20 light-years away, a frozen giant wandering alone. If one as massive as Jupiter strayed near us, its gravitational kick could send Uranus or Neptune spiraling inward, triggering a planetary domino effect that might one day fling Earth into deep space or straight into the sun. Yet rogue planets also hold tantalizing clues. Their icy surfaces could preserve pristine samples of ancient planetary material, untouched by stellar radiation. Some might even harbor exotic forms of matter, like superionic water, a bizarre state where water acts simultaneously as a solid and a liquid, theorized to exist under extreme pressures. And if life truly exists beneath their ice, it would prove that biology can thrive in the most unthinkable places, rewriting our definitions of habitability. The unsettling truth, we may never spot the one that matters most. Rogue planets are nearly invisible, emitting no light and reflecting almost none. The closest could be cruising through the Oort cloud right now, undetectable until its gravity starts bending the paths of distant comets, a subtle warning that our cosmic neighborhood has an uninvited guest. Whether bringers of life or chaos, these nomads remind us that the universe doesn't play by our rules. Stability is an illusion, and somewhere in the dark, a world without a star might already be heading our way. What if Earth's worst extinction events weren't random accidents but part of a cycle, orchestrated by a hidden executioner lurking in the dark? Enter Nemesis, the most infamous rogue planet never proven to exist. This theoretical object, nicknamed the Death Star, isn't just another icy nomad, it's a celestial serial killer, accused of slinging comets toward Earth every 26 million years like clockwork. The evidence comes from our planet's own scars. Fossil records reveal eerie patterns, mass extinctions recurring with unsettling regularity, from the dinosaurs' demise 66 million years ago to the Permian catastrophe 252 million years back, which wiped out 96% of all marine life. Each time the culprit seemed to arrive from deep space, the Nemesis theory paints a chilling picture. Imagine a brown dwarf or small red star, too dim to detect with 20th century telescopes, orbiting the Sun at a staggering distance, up to 1.5 light years away. This distant sibling, Nemesis, would follow an elliptical path so wide that every 26 million years, its gravity nudges the Oort cloud, that icy reservoir of comets at our solar system's edge. Like a cue ball striking a rack, Nemesis's pass would send thousands of comets screaming inward. Some miss, some burn up, but a few giant city-killer projectiles find Earth. Critics argue the statistics are fuzzy, the timing's not perfectly precise. Yet in 2010, NASA's WISE telescope scanned the sky for Nemesis and found nothing. No brown dwarf, no hidden star, but that doesn't close the case. Nemesis could be a rogue planet, ejected from its original orbit long ago, now drifting back periodically. Or perhaps it's not one object at all, but a cluster of dark, icy bodies collectively stirring the Oort cloud. The truth is, we've mapped less than 1% of the space within 3 light years of the Sun. A Nemesis-like object could still be hiding in the glare of the Milky Way stars, invisible until its next deadly visit. The implications are staggering. If Nemesis exists, its next awakening could already be underway. Right now, comets might be veering off course, their trajectories subtly bent toward the inner solar system. By the time we noticed, they'd be decades away, too late to deflect. But here's the twist: Nemesis isn't just a bringer of death. It could also be a cosmic librarian, preserving life's most ancient blueprints. Some theories suggest rogue planets like Nemesis act as interstellar arcs, ferrying frozen microbes between star systems. The same impacts that wipe out dominant species might also deliver new genetic material, sparking evolutionary explosions. Whether killer or catalyst, Nemesis forces us to confront a humbling truth. Earth doesn't orbit in isolation. We're part of a dynamic, violent system where unseen giants tug at the strings of fate. And somewhere out there, in the infinite dark, a shadow may be circling, patient, silent, and indifferent to the lives it reshapes with every pass. In the silent depths of space, 2 dead stars begin their final embrace. Neutron stars, the collapsed cores of once mighty suns, each so dense a single teaspoon of their material weighs as much as a mountain, are about to collide. This isn't just a collision, it's a cosmic alchemy experiment gone haywire. As they spiral toward each other at nearly light speed, their gravitational pull distorts spacetime itself, sending ripples across the universe. Then impact. The resulting kilonova explosion unleashes more energy in a few seconds than our Sun will produce in its entire lifetime. But the real magic and horror happens in the aftermath. Within the swirling maelstrom of superheated debris, atomic nuclei are ripped apart and reassembled under conditions so extreme they defy Earth-bound physics. Here, in this particle forge, the universe creates its heaviest elements: gold, platinum, uranium, the very metals that glitter in jewelry and power nuclear reactors. A single merger can produce hundreds of Earth masses worth of gold, flinging it into space like a cosmic treasure chest exploding, the gold in your wedding ring. It was likely born in the heart of such a cataclysm billions of years ago, but there's a dark side to this glittering spectacle. The same event that crafts precious metals also floods space with lethal radiation. Gamma rays, X-rays, and relativistic jets of plasma scream outward at near light speed. If a kilonova occurred within a few thousand light-years of Earth, the resulting gamma-ray burst could strip our ozone layer, trigger mass extinctions, and bathe the planet in deadly radiation for years. Even the gravitational waves from the collision, ripples in the fabric of spacetime first detected by LIGO in 2017, carry enough energy to subtly distort matter light-years away. Perhaps most unsettling is how quietly these disasters unfold. Unlike supernova, which light up galaxies, kilonovae are fleeting, bright for days, then gone. A neutron-star merger in our galactic backyard might go unnoticed until the radiation arrived, and they're more common than we once thought. New data suggests these collisions happen roughly once every 10,000 years per galaxy, meaning the Milky Way has hosted millions over its lifetime. Yet within this violence lies a paradox. Neutron-star collisions are both creators and destroyers. They scatter the elements necessary for life while wielding forces capable of erasing it. Their gravitational waves carry secrets about the nature of matter under conditions impossible to replicate on Earth. And they remind us that the universe's most beautiful gifts often come wrapped in fire and fury. A reminder that creation and destruction are two sides of the same cosmic coin. Deep in the cosmic void, something invisible flexes its muscles. Dark matter, the universe's hidden architect. While stars and galaxies steal the spotlight, these mysterious clouds of unseen mass shape the cosmos from the shadows, bending spacetime with their gravitational grip. Picture a ghostly hand reaching through a stellar nursery, its fingers made of particles we can't see or touch, yet strong enough to crush gas clouds into stars, or rip them apart before they're even born. These aren't just passive clumps of matter. Dark matter clouds operate like cosmic puppeteers, their gravity dictating where gas condenses and stars ignite. In the Large Magellanic Cloud, astronomers have observed regions where star formation runs wild, violent starbursts where hundreds of stars ignite simultaneously. The culprit, a dense dark matter cloud passing through, squeezing interstellar gas like an accordion until it collapses into fiery new suns. But the same force that creates can also destroy. In the Boötes Void, a region of space so empty it's been called the Great Nothing, dark matter may have strangled star formation entirely, its gravitational tides preventing gas from ever coalescing. The scariest part, we're swimming in them right now. The Milky Way's halo is thought to contain thousands of these invisible clouds, some as massive as dwarf galaxies. If one passed through our solar system, we wouldn't see it coming, but we'd feel the aftermath. Planets could tilt on their axes, their orbits subtly perturbed. Comets might be yanked from the Oort cloud and sent hurtling inward. Even Earth's core could experience strange tidal heating, triggering volcanic unrest. And because dark matter doesn't interact with light, our telescopes would register nothing but the unexplained gravitational ripples in its wake. Yet these enigmatic clouds aren't just agents of chaos, they're also cosmic glue. Without dark matter's scaffolding, galaxies would fly apart, their stars scattering like beads from a broken necklace. Some theories even suggest dark matter clouds preserve a memory of the universe's infancy, their distribution encoding secrets about the Big Bang itself. Their very existence challenges our understanding of physics, hinting at entire particle families beyond the standard model, shadowy building blocks that make up 85% of the universe's mass yet remain forever outside our perception. What makes dark matter truly unsettling isn't its power or its invisibility. It's the realization that we're living in a universe where the dominant form of matter is something we can't detect, only infer from its gravitational fingerprints. Every galaxy, every star, every planet exists in the web of these unseen giants, their silent dance shaping the cosmos in ways we're only beginning to comprehend. And somewhere out there, a dark matter cloud larger than 1,000 suns could be drifting toward an unsuspecting galaxy right now, poised to rewrite its destiny with nothing but the whisper of gravity. Imagine flipping a switch only to realize too late that the switch controls everything. That's the nightmare scenario hidden within one of quantum physics' most chilling theories, vacuum decay. Our universe as we know it might not be in its most stable state. Instead, it could be a precarious, false vacuum, balanced like a marble at the top of a hill. One tiny nudge, a high-energy particle collision, a black hole's gravitational ripple, even random quantum fluctuations, could send that marble tumbling into a lower energy state, rewriting the fundamental laws of physics in an expanding bubble of annihilation. This isn't science fiction. It's a legitimate, if speculative, consequence of how quantum fields behave. In simple terms, the vacuum of space isn't truly empty. It crackles with quantum energy, a seething foam of particles popping in and out of existence. Normally, this energy sits at a stable level like water settled at the bottom of a valley. But if our universe's vacuum is only metastable, a higher energy valley separated by an invisible hill, then all it would take is one quantum event to push it over the edge. The moment that happens, a sphere of true vacuum would form, expanding outward at the speed of light. Inside that bubble, the rules of reality would change instantly. Atoms might unravel, forces like electromagnetism or gravity could cease to function. Everything, planets, stars, even space-time itself, would be rewritten into something unrecognizable. Here's the terrifying part: we wouldn't see it coming. The bubble's boundary would move at light speed, giving zero warning. One moment, you're drinking coffee on Earth. The next, the edge of the bubble touches our solar system. And in the literal blink of an eye, your coffee, along with the cup, your hand, and the concept of coffee itself ceases to exist in any form we'd understand. The universe wouldn't end with fire or ice, but with a silent reconfiguration, like a cosmic reboot where the old code no longer runs. Could it happen tomorrow? Unlikely, but not impossible. Quantum physics allows for random, improbable events given enough time. Over trillions of years, the odds creep upward. Some theories suggest high-energy experiments like particle colliders could theoretically trigger vacuum decay, though the energy scales required are far beyond anything we can currently produce. Others speculate that cosmic rays or colliding neutron stars might act as catalysts in distant regions of space. Yet vacuum decay isn't just doom and gloom. It's a window into the deepest mysteries of the cosmos. The fact that our universe's vacuum has remained stable for 13.8 billion years hints that we might already be in the true lowest energy state. Or perhaps decay events are constantly happening in other quantum bubbles of the multiverse, their lethal borders forever out of reach beyond our cosmic horizon. Either way, the lesson is humbling. The fabric of reality might be more fragile than we ever imagined, held together by forces we're only beginning to decipher. And somewhere out there, in the infinite dark, the reset button might already have been pressed. At the heart of the galaxy M87, a monster stirs. A supermassive black hole with the mass of 6.5 billion suns, spinning like a cosmic turbine and hurling jets of plasma across space at 99% the speed of light. This is an active galactic nucleus, or a GN, the universe's ultimate power plant where gravity and magnetism conspire to create engines of destruction visible across billions of light years. Picture the violence at the core. Gas, dust, and even whole stars spiral toward the black hole's event horizon, heated to millions of degrees until it glows brighter than all the galaxy's stars combined. But the real horror happens above the poles, where twisted magnetic fields act like particle accelerators, cosmic railguns launching jets of ionized matter so powerful they punch straight through M87, stretching 55,000 light-years into intergalactic space. These jets aren't gentle streams, they're death rays sculpting the galaxy itself, sterilizing planets thousands of light-years from their path simply by bathing them in X-rays and relativistic particles. The damage isn't instant, it's methodical. Over millions of years, and a GN's radiation strips away atmospheres, boils oceans, and shreds complex molecules. Hubble telescope images reveal Fermi bubbles above galaxies like our Milky Way, ghostly remnants of past AGN eruptions where radiation once scorched entire galactic regions clean of life. Even more chilling, some quasars, the brightest AGNs, emit enough high-energy photons to theoretically prevent star formation across entire galaxy clusters, turning thriving cosmic neighborhoods into stagnant graveyards over cosmic timescales. Yet there's twisted beauty in the chaos, a GNS-shaped galactic evolution, their outflows enriching intergalactic space with heavy elements forged in their accretion disks. Some theories suggest they regulate star formation, preventing galaxies from burning through their gas too quickly, and their jets, observed in radio telescopes as brilliant beacons, act as cosmic yardsticks, helping astronomers measure the universe's expansion. The unsettling truth, our Milky Way has its own dormant AGN Sagittarius, a star. While quiet now, evidence suggests it flared violently 2 million years ago, a burst so bright it left scars on Magellanic cloud gas clouds visible today. One day it could awaken again. If it does, Earth's fate would hinge on one question: are we staring down the barrel of the gun or safely out of the line of fire? Active galactic nuclei remind us that even galaxies have lifespans, their stories written in the interplay of creation and destruction. And somewhere in the night sky, another AGN might be flickering to life right now, its jets aligning with some unsuspecting world billions of light-years away, a fate we can observe but never escape. The universe might be threaded with invisible scars, leftover defects from the explosive birth of spacetime itself. These are cosmic strings, hypothetical fissures in reality, so thin they'd be narrower than a proton, yet stretching across billions of light-years like cracks in a frozen lake. Born in the first chaotic moments after the Big Bang, when the fabric of spacetime underwent violent phase transitions, these defects would carry unimaginable density. A single inch of cosmic string could outweigh Mount Everest. Picture one drifting through a star system. At first, nothing seems amiss until the string's immense gravity warps light from distant stars like a funhouse mirror, creating identical copies of celestial objects in a phenomenon called gravitational lensing. But the real horror lies in its interaction with matter. A cosmic string wouldn't just bend spacetime, it would slice through planets and stars like a wire through cheese, its passage leaving two perfectly cleaved halves drifting apart. The cut would be so clean, so instantaneous that atmospheres wouldn't have time to leak, oceans wouldn't slosh, just a silent, surgical division of everything in its path. The strangest part, these strings wouldn't obey the rules we're used to. Some theories suggest they could form loops, vibrating at near light speed and emitting bursts of gravitational waves detectable across the universe. Others propose they might be superconducting, carrying electric currents strong enough to power entire galaxies. And if two strings crossed, the collision could release enough energy to briefly outshine a quasar, twisting spacetime into knots that ripple outward for eons. Yet the most unsettling possibility is that we might already be entangled in one. A cosmic string passing through Earth wouldn't announce itself with fanfare. We'd notice only subtle anomalies, sudden shifts in satellite orbits, unexplained temperature gradients in the upper atmosphere, or bizarre quantum fluctuations in particle colliders. By the time we pieced together the cause, the string could be light years away, its damage already done. Cosmic strings remind us that the universe's infancy was a violent, messy affair, and some of its relics might still lurk in the dark, remnants of a time when reality itself was still cooling into shape. They're not just theoretical curiosities, They're potential proof that the cosmos is far stranger, far more fragile than we ever imagined. And if they exist, their silent blades could be drifting through the void right now, slicing unseen through galaxies, stars, and the empty spaces between. Most stars die quietly, fading into darkness, but not pulsars. These spinning neutron stars are the universe's lighthouse beacons, pulsing with deadly precision. Born from supernova explosions, they pack a sun's worth of mass into a city-sized sphere, spinning so fast their surfaces can reach speeds of 40,000 miles per hour. What makes them truly terrifying isn't their density or speed, it's their beams. Twin jets of radiation, focused tighter than a laser, scream into space from their magnetic poles. And if one of those beams ever sweeps across Earth, the consequences would be catastrophic. Take the Crab pulsar, the corpse of a star whose explosion lit up Earth's skies in 1054. Even today, 950 years later, it spins 30 times every second, shooting out X-rays and gamma rays with every rotation. Those beams carry enough energy to strip electrons from atoms, shredding DNA and frying electronics at a distance of hundreds of light years. If the Crab Nebula were closer, say, 50 light-years instead of 6,500, its pulsar's radiation would ionize our atmosphere within hours, triggering continent-wide blackouts and spiking cancer rates like a silent, invisible nuclear war. Here's how the nightmare unfolds. As the pulsar's beam sweeps past Earth, the first wave would be electromagnetic chaos. Radio communications fail, GPS satellites glitch. Power grids overload as surges rip through transformers, plunging cities into darkness. Then comes the biological toll. The radiation would penetrate deep into human tissue, causing acute radiation sickness at best, irreversible mutations at worst. Over months and years, the cumulative damage would unravel ecosystems, sterilizing crops and triggering mass extinctions. But pulsars aren't just indiscriminate killers, they're precision instruments. Their beams are so finely focused that even a slight misalignment means the difference between apocalypse and a near miss. The Vela pulsar, for example, spins 11 times per second with beams angled just wide enough to spare Earth. For now, pulsars slow down over millennia, their beams wobbling like a top losing momentum. One day, Vela's death ray might drift into alignment, or a closer, younger pulsar could emerge from the cosmic dark with its sights already set on us. Strangely, these same lethal beams make pulsars cosmic timekeepers. Their pulses are so regular they rival atomic clocks, allowing astronomers to map the galaxy's magnetic fields and test Einstein's relativity theories. Some even carry planetary systems, frozen worlds bathed in eternal, lethal light, where hypothetical life would need to evolve underground or under miles of ice. The chilling reality: there could be thousands of pulsars in our galactic neighborhood we haven't detected yet. Many point their beams away from us, silent and invisible until their alignment shifts. Others might be hidden behind dust clouds, their radiation muted but not gone. Pulsars remind us that the universe doesn't need malice to be deadly, just bad luck. And somewhere out there, a spinning remnant of a dead star might already have Earth in its crosshairs, waiting for its next pulse to fire. The shockwave from a kilonova doesn't just fade into the cosmic background, it carves a path of destruction light-years wide, a tsunami of supercharged particles and radiation that rewrites the rules of physics for anything in its way. Picture the aftermath of two neutron stars colliding. The initial explosion blasts a fireball of ultra-dense matter outward at nearly light speed, but the real devastation comes from the shrapnel. Chunks of neutron-rich material, some weighing more than Earth, get hurled into space like cosmic shrapnel, trailing streams of radioactive isotopes behind them. These debris clouds aren't just expanding, they're mutating. As the material plows through interstellar gas, it triggers secondary shockwaves, heating the surrounding hydrogen to millions of degrees and igniting brief, artificial stars along its path. Any planet within a few light years wouldn't just be bathed in radiation, it would be scoured. The initial gamma-ray burst might strip its atmosphere, but the kilonova's afterglow, a mix of X-rays, ultraviolet, and high-energy protons, would bombard the surface for centuries, turning oceans into steam and crust into molten slag. Even worse, the debris is laced with heavy elements like uranium and plutonium, raining down radioactive contamination that could persist for millions of years. The universe has seen this horror before. In 2017, the LIGO Observatory detected gravitational waves from a neutron star merger labeled GW170817. Follow-up observations revealed something startling. The event had ejected a plume of gold and platinum totaling several hundred Earth masses, but it also spewed a jet of charged particles moving at 99.9% light speed. Had that jet been aimed at a nearby star system, the sheer kinetic energy alone would have vaporized planets down to their cores. Yet kilonovae aren't just destroyers, they're also cosmic alchemists. The same shockwaves that sterilize worlds also forge the rarest elements in the universe. Elements like gold, platinum, and neodymium are born in these cataclysms, their atoms fused together in the heart of the expanding fireball. Over millennia, these metals drift through space, eventually seeding new generations of stars and planets. That means the gold in your jewelry, the uranium powering reactors, even the iodine in your thyroid, all of them were once blasted into the void by a kilonova's fury. The chilling takeaway: we might owe our existence to one of these explosions. Billions of years ago, a kilonova's debris could have enriched the cloud of gas that later formed our solar system, gifting Earth with the heavy elements necessary for life. But the same process that gave us these gifts could also take them away. If a neutron star merger happened within a few thousand light years today, its shockwave would reach us with no warning, a silent, invisible storm front rewriting the chemistry of our atmosphere and oceans before we even knew it was coming. The universe doesn't distinguish between creation and destruction. It simply moves forward, leaving us to navigate the aftermath. Some black holes aren't born from dying stars, they're relics of creation itself. Primordial black holes could be lurking in the cosmos right now, microscopic remnants of the Big Bang's violent infancy. Imagine the universe in its first second, a seething cauldron of energy and pressure so extreme that random density fluctuations collapse directly into black holes, some as small as atoms, others as massive as planets. Unlike their stellar counterparts, these ancient objects didn't need stars to die. They were forged in the chaos of existence itself, the scariest part. They might be closer than we think. If primordial black holes exist, they could be drifting through our solar system undetected, their tiny event horizons smaller than a proton but packing the mass of a mountain. One could pass through Earth right now, and we'd only notice the aftermath: strange seismic waves with no epicenter, sudden temperature spikes along an invisible path, or a trail of radiation where atoms were shredded by tidal forces. Some theories even suggest these black holes could account for dark matter, hiding in plain sight while their gravity sculpts galaxies, but their true danger lies in their expiration date. Thanks to Hawking radiation, smaller black holes don't last forever, they evaporate, and the tinier they are, the faster they explode. A primordial black hole with the mass of an asteroid would finally detonate with the force of 1 billion nuclear bombs, releasing all its pent-up energy in a gamma-ray flash. If one were decaying near Earth, we wouldn't just see a light show. We'd be bathed in lethal radiation, our atmosphere ionized, our electronics fried. Yet these enigmatic objects aren't just ticking bombs, they're time capsules. A primordial black hole surviving to the present day would carry pristine information about the universe's first moments, its evaporation offering physicists a glimpse beyond the Big Bang's veil. Some researchers even propose hunting for them by watching for stars that inexplicably flicker, their light bent by an invisible, ancient passerby. Whether killers or cosmic artifacts, primordial black holes force us to confront a humbling idea. The universe might be filled with unseen ghosts left over from creation's first breath. And some of them could be right next door. Most stars die with a bang, but hypernovas go out with an apocalypse. These aren't just supernovas, they're supernovas on steroids, explosions so violent they rewrite the rules of stellar death. Picture a star 30 times more massive than our Sun, its core collapsing not into a neutron star but straight into a black hole. The resulting shockwave doesn't just blast outward, it gets funneled into twin jets of plasma hotter than a billion suns, drilling through space at nearly light speed. This is a hypernova, nature's ultimate particle accelerator, capable of emitting more energy in seconds than our entire galaxy does in a year. Then there's the even rarer nightmare, pair instability supernovas. These occur in stars so massive between 140 and 260 solar masses that their cores become furnaces of antimatter. Under such extreme heat and pressure, gamma rays inside the star spontaneously convert into electron-positron pairs, robbing the core of its stabilizing radiation pressure. The star's heart skips a beat, then collapses in on itself, not into a black hole but into runaway thermonuclear detonation. The explosion is so powerful it completely obliterates the star, leaving no remnant behind. No neutron star, no black hole, just an expanding fireball bright enough to outshine entire galaxies for months. The danger isn't just the light show, it's the afterglow. Both hypernovas and pair instability supernovas unleash torrents of ultraviolet radiation, a silent killer capable of igniting planetary atmospheres from hundreds of light years away. Models suggest the UV flash from a hypernova within 25 light years could turn Earth's skies into a global blowtorch, splitting nitrogen and oxygen molecules apart to form nitric oxide, a compound that would then rain down as acid. Oceans would acidify, ozone layers would evaporate, and any exposed life would suffer radiation burns akin to standing next to a nuclear bomb. We've likely seen this horror before. In 2006, astronomers detected SN 2006 Gi, a supernova 100 times brighter than normal. Its light curve suggested a pair instability explosion, a stellar suicide so complete it scattered 50 solar masses worth of iron into space, enough to forge a million Earths. Even more chilling, some theories suggest the Ordovician extinction 450 million years ago might have been triggered by a nearby hypernova's gamma ray burst followed by its UV flash, slowly cooking the planet over centuries. Yet these cataclysms are also cosmic crucibles. Hypernovas are thought to forge the universe's heaviest elements, from gold to uranium, while pair instability explosions may have seeded early galaxies with the iron needed for rocky planets. Their violence shapes the cosmos, triggering star formation in distant gas clouds and illuminating the darkest corners of the universe, the unsettling truth. We may already be in the crosshairs. Eta Carinii, a binary star system 7,500 light-years away, contains a hypergiant on the verge of collapse. If it goes hypernova, its UV flash would reach Earth with the brightness of a full moon. Beautiful to observe, but a stark reminder that we're floating in a shooting gallery where the next cosmic detonation could already be counting down. The universe doesn't warn before it strikes. It simply burns, destroys, and recreates, with or without witnesses. Galaxies don't just sit quietly in the void. Some scream across space with the force of a billion hurricanes. Galactic superwinds are the universe's ultimate storms, blasting outward from star-forming regions at speeds that defy comprehension. Picture a starburst galaxy like M82, where stars are born in such frenzied clusters that their combined radiation and supernova explosions create a pressure cooker of chaos. The energy builds until it can no longer be contained, erupting in a torrent of superheated gas, a wind so powerful it reaches velocities of 2,000 kilometers per second, fast enough to cross the continental United States in less than 2 seconds. These aren't gentle breezes. Superwinds act like cosmic sandblasters, stripping smaller satellite galaxies of their star-forming material and leaving behind barren wastelands. The dwarf galaxies orbiting starburst systems often bear the scars twisted, gas-deprived husks where new stars can no longer ignite. Even more terrifying, the winds don't just stop at the galaxy's edge. They punch into intergalactic space, dragging heavy elements like oxygen and iron with them, seeding the cosmos with the raw materials for future worlds. But that generosity comes at a cost. Any planetary system caught in the path would face an invisible tsunami of charged particles, its atmosphere scoured away like dust in a sandstorm. The scale is almost impossible to grasp. In the antennae galaxies, two colliding systems unleashing a superwind, the outflow stretches over 300,000 light-years, 3 times the diameter of the Milky Way. Within that maelstrom, temperatures soar to millions of degrees, hot enough to vaporize planets instantaneously. Yet these same cataclysmic outflows might be the reason life exists at all. Without superwinds enriching the cosmos with heavy elements, planets like Earth and the atoms that compose us might never have formed. But here's the chilling twist: superwinds can also strangle the galaxies that birthed them. By ejecting gas too violently, they risk starving themselves of the fuel needed to make future stars. It's a cosmic catch-22. The same process that spreads life-giving elements can also doom a galaxy to slow stagnation. Some astronomers believe our own Milky Way experienced a superwind phase billions of years ago, a tempest that shaped its evolution and left behind the galactic neighborhood we see today. What makes these phenomena so unsettling isn't just their power, it's their invisibility. A superwind could be blowing through our corner of space right now, and we'd have no way of knowing until its effects became undeniable. The universe doesn't announce its fury with flashing lights. It simply moves, destroys, and creates in the same breath, a reminder that even the emptiest stretches of space are alive with forces beyond our control. If black holes are the universe's insatiable vacuums, white holes might be its cosmic fire hydrants, theoretical geysers where space itself erupts in a violent outpouring of matter and energy. Unlike their dark counterparts, which trap everything past the event horizon, white holes defy gravity's pull by violently rejecting anything that comes near. Imagine a singularity in reverse. Instead of collapsing inward, it explodes outward, spewing light, gas, and particles at speeds that make supernova look sluggish. These aren't just mathematical oddities. They could be remnants of the Big Bang itself, frozen fragments of creation suddenly awakening to rewrite the rules of spacetime. The mechanics are mind-bending. According to general relativity, a white hole is the time-reversed twin of a black hole. Where a black hole's event horizon marks a point of no return, a white hole's horizon is a no-entry zone. Anything inside can escape, but nothing outside can enter. Some theories suggest they could form when a black hole's singularity punches through the fabric of spacetime, emerging elsewhere like a wormhole's exhaust vent. Others propose they're primordial, relics from the universe's birth that have been locked until now, waiting for some quantum trigger to unleash their pent-up energy. The spectacle would be unlike anything in nature. A white hole's eruption wouldn't just release matter, it would rewrite local physics. Space-time around it would warp so severely that time itself could appear to stutter or loop. Radiation would flood outward in lethal waves, sterilizing nearby star systems in a heartbeat. And the debris, chunks of exotic matter, forged under conditions impossible in our universe, might rain into space with unpredictable properties. Some models even suggest these outbursts could briefly outshine entire galaxies, their light visible across cosmic distances as a beacon of annihilation. Yet white holes remain ghosts in the equations. No confirmed observation exists, and many physicists argue they're mathematical curiosities rather than real objects. But the universe has surprised us before. Gamma-ray bursts, once thought implausible, are now routine detections. If a white hole did flare to life, the signs would be unmistakable. A sudden, point-like explosion of high-energy particles with no apparent source, followed by a cooling afterglow rich in heavy elements. Some astronomers speculate that certain ultra-luminous supernova or fast radio bursts could be white holes in disguise, cosmic fireworks masquerading as more mundane phenomena. The implications are staggering. A nearby white hole eruption could bathe Earth in radiation powerful enough to strip our atmosphere or mutate DNA across entire ecosystems. But on a cosmic scale, these explosions might also be the universe's recycling centers, gathering entropy in one place and discharging it elsewhere to balance the books. They could even serve as natural particle accelerators, creating conditions so extreme they reveal the secrets of quantum gravity. White holes challenge our deepest assumptions about cause and effect. If they exist, they're proof that the universe isn't just expanding, it's constantly rewriting its own rules. And somewhere in the void, one might be counting down to its grand finale, a detonation that could reshape reality itself without warning. The cosmos doesn't just create and destroy in cycles. It reinvents, leaving us to piece together the fragments of its endless experimentation. Picture the expanding universe not as a gentle balloon inflating, but as a dark ocean with hidden whirlpools where the currents suddenly accelerate to nightmare speed. These are dark energy vortexes, theoretical regions where the mysterious force accelerating cosmic expansion runs wild, twisting space-time into frenzied knots that could rip apart reality itself. Most of the cosmos expands uniformly, but in these anomalies the rules break down. Galaxies aren't just drifting apart, they're being violently shredded, their stars flayed into streams of light as the fabric between them stretches beyond the limits of matter. The math behind these vortexes reads like a horror story. Dark energy, which makes up 68% of the universe, typically exerts a gentle negative pressure that pushes galaxies apart. But in extreme scenarios, perhaps near primordial spacetime defects or overlapping quantum fields, its influence could concentrate into spinning maelstroms where expansion accelerates exponentially. The effect would resemble a localized preview of the Big Rip, the hypothetical endgame where dark energy tears apart atoms. Galaxy clusters caught in these vortices wouldn't just drift away. They'd undergo spaghettification, stretched into celestial noodles by tidal forces stronger than any black hole's grip. Evidence might already lurk in our observations. Astronomers have mapped peculiar cold spots in the cosmic microwave background, regions slightly emptier than expected, as if something had scooped out matter and energy. Some theorists propose these voids could be scars from ancient dark energy vortexes, areas where expansion temporarily went rogue and erased everything in its path. Others point to bizarre supercluster arrangements, like the Laniakea supercluster's filamentary tendrils, which look less like natural structures and more like taffy pulled apart by invisible hands. The terrifying implication: these vortexes might not stay in the distant cosmos. If one formed near the local group, our galactic neighborhood, the consequences would be grotesquely poetic. First, the Milky Way and Andromeda would begin separating unnaturally fast, their impending collision cancelled by an unseen force. Then, gravity itself would start losing, stars wrenched from their orbits, planets torn from their suns, and eventually, even atomic bonds failing as the vortex's event horizon of expansion reached our doorstep. The end wouldn't come with fire or ice, but with silent, inexorable thinning, as every molecule in your body was pulled apart by the stretching of space itself. Yet within this apocalypse lies a tantalizing clue. Dark energy vortexes could be the universe's way of revealing its true nature. If we could observe one, its behavior might crack open the secrets of quantum gravity or expose hidden dimensions. Some models even suggest these phenomena could be wormholes to other epochs, not tunnels through space, but through time, where the universe's accelerated expansion in one region bridges to its inflationary birth in another. The ultimate irony, dark energy vortexes might be both destroyers and creators. Just as they annihilate structure, they could also seed new universes in their wake, their violent expansion birthing bubble realities with entirely different physics. We might be living in the aftermath of such an event, our cosmos just one eddy in an infinite cascade of others, each torn apart and reborn by the same dark forces we're only beginning to name. The universe doesn't just expand its experiments, and sometimes those experiments dissolve the very lab they're conducted in. Out in the void between stars, a new kind of doomsday weapon might be drifting, not one that explodes, but one that rewrites the very rules of matter itself. These are strange matter asteroids, rogue space rocks laced with exotic strangulates, hypothetical chunks of quark-gluon plasma so stable they could turn ordinary atoms into copies of themselves upon contact. Picture a single pebble-sized fragment of this stuff striking Earth. Within hours, mountains could begin collapsing in on themselves as their atoms reconfigure into ultra-dense strange matter, triggering a chain reaction that converts the entire planet into a lifeless, city-sized ball of degenerate quarks. The nightmare scenario starts with neutron stars. Under unimaginable pressure, their cores may contain strange matter, a superfluid where up, down, and strange quarks mingle freely instead of forming protons and neutrons. Normally, this exotic state stays contained by the star's gravity, but if two neutron stars collide, fragments could be ejected like cosmic shrapnel, some cooling into stable strangulates that drift for eons until colliding with an unfortunate world. The physics is chillingly simple. Strange matter's binding energy per particle is lower than normal matter's, making it the ultimate ground state of reality. Like water flowing downhill, any matter touching it would melt into the same exotic configuration in a runaway process called the strange matter catastrophe. We've seen hints of this danger in the lab. Particle accelerators like the relativistic heavy ion collider have briefly recreated quark-gluon plasma, though thankfully at energies too high to form stable strangulates. But the universe operates on different scales. In 1988, physicist Edward Witten calculated that if even one stable strangulate exists in nature, it could have already converted entire galaxies into strange matter over cosmic time. The fact that we still see normal matter suggests strangulates are either incredibly rare or their conversion process isn't as efficient as feared, yet the risk isn't zero. Some pulsars exhibit glitches in their spin rates that could hint at strange matter interiors occasionally cracking the neutron star's surface. A handful of ultra-dense meteorites recovered on Earth, like the decay meteorite analyzed in 2003, show isotopic anomalies that a few researchers speculate could be fragments of strange matter. Most scientists dismiss these as measurement errors, but the unsettling possibility remains. What if we've already been hit by strangelet containing space debris, and only luck prevented a planetary-scale infection? The ultimate horror lies in the ambiguity. Unlike gamma-ray bursts or asteroid impacts, a strange matter contagion wouldn't announce itself with fireworks. The conversion would spread silently at the atomic level, radiating outward from the impact site at roughly the speed of sound in rock. By the time seismic sensors registered continent-wide sinking anomalies as Earth's crust densified, it would already be too late. There'd be no evacuation, no defense, just the slow, inevitable transformation of every mountain, ocean, and living cell into something fundamentally alien. But here's the cosmic irony. Strange matter might also be the key to revolutionary technologies. If harnessed safely, its superconducting properties could enable room-temperature superconductors or compact energy storage. Some theories even propose using it to stabilize wormholes for interstellar travel. The universe doesn't deal in pure danger or pure benefit. It offers raw materials, leaving it to chance and intelligence to determine whether they become tools or extinction events. Whether destroyers or cosmic curiosities, strange matter asteroids force us to confront an unsettling truth. The boundary between physics and nightmare is thinner than we'd like. Out there in the dark, a single speck of misconfigured quarks could be drifting toward us right now, carrying the potential to erase the world we know, or reveal an entirely new one. Most stars fade quietly into the afterlife as cooling white dwarfs, but sometimes the dead refuse to stay buried. Zombie stars, cosmic anomalies defying the natural order, are stellar corpses that violently reanimate when gravity grants them a second life. Among the most unsettling are helium white dwarfs, the prematurely dead remnants of stars stripped of their outer layers before they could burn through their nuclear fuel. These dense, Earth-sized embers should cool into oblivion until a cosmic collision or merger shocks their core back to life, triggering explosions powerful enough to outshine entire galaxies. Take the case of SN 2002-CX, a so-called Type IX supernova that baffled astronomers with its peculiar dimness. Unlike the standard thermonuclear detonation of a white dwarf, this explosion left part of the star intact, a half-dead, half-alive abomination still burning amid the wreckage. The culprit, a helium white dwarf, siphoned gas from a companion until it reached critical mass, but instead of fully detonating, it underwent a partial explosion that left its core smoldering like a cosmic campfire. These failed supernovas create stellar Frankensteins, objects neither dead nor truly alive, caught in a grotesque limbo between existence and annihilation. But the true horror unfolds when two zombie stars collide. In dense stellar graveyards like globular clusters, white dwarfs occasionally spiral into catastrophic mergers. When two helium white dwarfs smash together, their combined mass reignites nuclear fusion in a heartbeat, not with the steady burn of a living star, but with the unstable frenzy of a reanimated corpse. The result is a Aya supernova, an explosion a tenth as bright as a typical supernova but far more unpredictable. Some fizzle into black holes, others detonate with enough force to birth neutron stars. Unlike normal supernova, these events leave no recognizable corpse behind, just an eerie absence where physics as we know it breaks down. The danger isn't just their violence, it's their deception. Zombie stars masquerade as harmless embers for billions of years before suddenly erupting. In 2016, astronomers spotted a helium white dwarf in the Milky Way's halo with a surface temperature of 40,000 degrees, far hotter than such a corpse should be. The likely explanation: it recently cannibalized another white dwarf, reheating itself like a vampire draining fresh blood. If a similar object lurked within a few hundred light years, its resurrection could bathe our solar system in lethal radiation before we'd even identified the threat. Yet these undead stars aren't just destroyers, they're cosmic recyclers. Their peculiar explosions forge rare isotopes like calcium and titanium, scattering them into space to form new planets and life forms. The same collisions that birthed them might also create black dwarf supernova, in the far future theoretical explosions of white dwarfs that finally cool after trillions of years, only to detonate when quantum tunneling reignites their cores. The lesson is clear: in the universe, death is rarely permanent. Gravity writes the rules, and sometimes it cheats, reanimating stellar cadavers into monsters that burn, explode, and collapse under the weight of their own second chances. And somewhere in the dark, a zombie star might already be stirring, ready to remind the cosmos that nothing stays buried forever. Our galaxy is caught in a cosmic current, a silent river of space-time pulling us toward something we can't see, an invisible maelstrom called the Great Attractor. At 14 million miles per hour, the entire Milky Way and its neighboring galaxies are racing toward this gravitational anomaly, a region so dense it bends the paths of light itself. This isn't just a gentle drift, it's a headlong plunge into the unknown, drawn by a force strong enough to reshape the fate of entire galactic clusters. The mystery begins with X-rays. In the 1970s, astronomers mapping the cosmos noticed something strange. Hundreds of galaxies, including our own, were all streaming toward a single point in the constellation Centaurus. But when they looked there, they found nothing, just a void, an apparent emptiness exerting the gravitational pull of tens of thousands of Milky Ways. The Great Attractor wasn't just invisible, it was hidden behind the thick dust and stars of our own galaxy's disk, a cosmic blind spot we've only recently begun to peer through. What we've uncovered is unsettling. The attractor isn't one object, but a sprawling supercluster called the Norma Cluster, a knot of galaxies 300 million light-years wide, wrapped in dark matter so dense it acts like a gravitational whirlpool. At its heart lies Abell 3627, a galaxy cluster so massive its gravity distorts spacetime into a lens, bending the light from galaxies behind it into ghostly arcs. But even this doesn't fully explain the pull. There's something deeper, heavier, perhaps a confluence of dark matter filaments weaving the entire region into a gravitational snare. The danger isn't the journey, it's the destination. As galaxies spiral toward the Great Attractor, they don't just drift, they collide. The Norma Cluster is a graveyard of galactic wreckage, where galaxies smash together at millions of miles per hour, their stars flung into chaos. Gas clouds compress, igniting furious bursts of new stars, while supermassive black holes merge, sending gravitational shockwaves rippling through spacetime. Our local group of galaxies, including Andromeda and the Milky Way, could one day face the same fate, torn apart and reassembled in this cosmic forge. Yet the Great Attractor might not even be the end of the line. Recent observations reveal an even larger structure behind it, the Shapley supercluster, a monster collection of galaxies pulling the attractor itself. We're caught in a nested series of currents, each dragging us toward something grander and more mysterious. It's a humbling reminder the universe doesn't revolve around us. We're just passengers on a voyage whose final destination remains hidden in the dark. The beauty of this enigma is what it reveals about our place in the cosmos. The Great Attractor isn't destroying galaxies, it's weaving them into something new. A tapestry of matter and energy being stitched together by gravity's invisible hand. One day, billions of years from now, our descendants, if they still exist, might gaze up at a sky transformed, their galaxy reshaped by forces set in motion long before Earth even formed. The universe doesn't care about our timelines. It moves, merges, and rebuilds on scales we can barely fathom. And the Great Attractor is just one thread in its infinite design. From rogue black holes drifting unseen through our solar system to magnetars capable of sterilizing planets with a single cosmic tantrum, we've journeyed through the universe's most terrifying phenomena. Now, let's rank these nightmares by their true existential threat, how likely they are to end life as we know it. Topping the list, vacuum decay, the silent rewrite of reality itself, where physics could unravel without warning. Close behind, gamma-ray bursts, nature's ultimate sniper rifles and hypervelocity stars, celestial bullets already en route to unknown targets. Then come the slow burn threats, dark energy vortexes stretching spacetime to its breaking point, or the Great Attractor pulling galaxies toward an invisible galactic meat grinder. Mid-tier dangers include zombie stars resurrecting in catastrophic explosions, kilonova shockwaves scattering radioactive shrapnel across light years, and strange matter asteroids that could transform Earth into a lump of degenerate quarks. Don't underestimate primordial black holes, tiny but deadly. They might be passing through you right now. Meanwhile, active galactic nuclei and quasars rank lower only because their death beams are currently misaligned, while pulsars and cosmic strings are lethal but localized threats. Even rogue planets and hypothetical Nemesis objects, while chaotic, lack the instant kill factor of their cosmic cousins. So where does that leave us? Alive against astronomical odds, we orbit in a fragile sweet spot far enough from these horrors to survive, yet close enough to study them. But the universe never guarantees safety. It's a clockwork nightmare where any second could bring a planet-sterilizing pulse or a space-time rending singularity. Which of these cosmic monsters keeps you up at night? The invisible hand of dark matter sculpting galaxies, or the white hole waiting to erupt in our backyard? Drop your worst nightmare in the comments and stay tuned. Next time, we'll explore humanity's desperate, ingenious plans to survive these apocalypses, from asteroid deflection to black hole escape pods. Until then, remember, the cosmos doesn't hate us. It simply doesn't care, and that's infinitely more terrifying.